This work presents Learned Model Predictive Game for multi-agent drone racing. While much of the recent research in autonomous racing has focused on optimizing single-agent performance, such as minimizing lap times, real-world racing scenarios often involve multiple competitors. This creates a dynamic, multi-agent environment where decision-making is influenced by the actions of other participants. We formulate this task as a two-player, non-cooperative dynamic game solved over a receding horizon, where each player aims to minimize their own objective. Due to the non-cooperative nature of the task, each agent's optimal strategy is contingent upon their opponent's actions. In this setting, the Model Predictive Game Planner solves a coupled optimization problem to identify a Nash equilibrium. This represents a strategy profile where no player can reduce their individual cost by unilaterally deviating, effectively anticipating the opponent's best response. However, finding this equilibrium requires computationally demanding solvers. A standard approximation is to decouple the problem, leading to an MPC baseline. It treats the opponent as a non-reactive dynamic obstacle with a fixed velocity profile, reducing the game to a single-player optimization problem. When we compare these two approaches in head-to-head racing, distinct performance patterns emerge. At moderate velocities, the strategic reasoning of MPG yields superior performance. By explicitly modeling coupled dynamics, the MPG agent can execute interaction-aware maneuvers that the standard MPC fails to anticipate. However, as speeds increase, the computational cost of the game-theoretic solver becomes a critical bottleneck. Because the physical state evolves during the computation time, the calculated strategy is often outdated by the time it is applied. Our experiments demonstrate that at high speeds, this computational latency negates the strategic advantage of MPG, often resulting in lower win rates compared to the reactive MPC. To address this trade-off, we introduce Learned MPG, which solves the dynamic game by leveraging an amortized game formulation to accelerate computation. More specifically, LMPG amortizes the computation of receding horizon game solutions by training a structured neural network for each player eye that predicts their Nash strategy given the current state. We evaluate these methods in a head-to-head tournament, spanning both simulation and physical hardware experiments. The results confirm that LMPG successfully mitigates latency-induced suboptimality. It outperforms both baselines in high-speed scenarios, enabling robust interaction-aware racing in real time. To test generalizability, we train LMPG Gen by aggregating experience from 4 morphologically diverse tracks and evaluate it on a track unseen at training time. We evaluate LMPG Gen against an MPC variant utilizing a more sophisticated opponent prediction model, finding that LMPG Gen consistently outperforms it even when deployed zero-shot.